we are lucky to have Gregor, who's going to give us a talk on boundary data meets bound states. And I'll just ask that everyone keeps their microphones muted, although I'm sure Gregor won't mind some questions if anyone has any, but maybe we could try using the raise hand thing. I don't know if that ever works, but we can give it a try.
Let's see.
Anyway, take it away.
Okay, thanks a lot. Yeah, so thanks a lot for the invitation, first of all, that you share some of your time with me, that I can talk a little bit about my work. Today, I will try to mostly talk about these two papers here I've been doing with Rafael Porto at the end of last year. The main idea is that we try to make the connection between some gravitational scattering problem and how we can extract data from let's say scattering amplitudes and explain this more orbital-like problem, which is very important for gravitational waves. So of course, this is somehow the main motivation of this whole story, that you would like to study this type of problems a little bit closer. So since a couple of years ago, that have been the first detections of gravitational waves, of course, there's a lot of interest has been raising to compute this type of amplitude, this type of problems, also from the theory side. So as you see here, this is actually a numerical relativity simulation from Alessandro Bonanno and Osokine. And the important part here is that this problem is very hard to solve in general. And it all boils down, of course, the nonlinearity of the Einstein's equation. Some feedback. Someone turn on his audio because I hear myself. Okay, it's better. Thank you. Okay. All right. So mainly, this process is very often described and broke down into three phases. There's first of all, we'll have this in spiral phase. There's a merger phase where these bodies come very close together, and at the end of the day, these two bodies merge. We just have some fluctuations of this final state of the bodies. This process is very similar independently of what type of object you're actually looking at. So either you can have some black hole scattering that you look at, black hole merger, even a black hole neutron star, neutron, whatever you want. The generic setup is in principle very similar. At the end of the day, what everyone wants to get is this type of waveforms here. So that's what actually LIGO, Virgo, and all the other laboratories are measuring, and that's what you want to get. So to describe this, for this in spiral phase here, what is usually done is that it has to be done analytically. So there's a big problem actually if you try to just simulate it numerically. Because for example, so I heard a talk by Scott Noble some time ago, and he said that if they just want to get one data point, so for just one input configuration of your black holes, some mass configurations and starting impulse configuration, for just to get around 400 cycles, it takes half a year on their NASA supercomputer. So really this in spiral phase, they can actually take a lot of cycles. So the new telescope LISA will measure up to 1,000, 2,000 cycles. And that's why it's almost impossible to really simulate it in any feasible way. And that's the merger ring down just afterwards, but the rest then afterwards would just be about this in spiral phase and how we can efficiently describe this whole process. So the goal is most of the time that you want to get to compute some effective two-body Hamiltonian. So the easiest way to start, you just have some conservative potential. So you just forget about any type of gravitational radiation that you have. You just have some two point-like sources that spiral around each other, or you want to somehow find what's the effective gravitational potential between these two guys. It's often organized in two different ways. So first of all, you have an expansion in the gravitational coupling. This could be G Newton to some powers. And then in the other direction, towards the right, we can organize it in powers of the velocity, so of the relative velocity between these two bodies. Now, this problem has a lot of different aspects. So as I said, you would start with the simplest one, would be the conservative potential. Then you can start adding spins to your object, so arbitrary spin. So actually, by the way, everything we're talking about here is just classical gravity. So there won't be any, I don't consider any quantum effects or anything. So it's just purely Einstein, classical Einstein in gravity. Of course, if you then really want to describe the whole problem over here, you will have to think about radiation, that these bodies actually get closer, they lose energy and get closer and closer to each other. So we'll have to also include some radiational part of your gravitational interaction into your, well, let's say it's now a three-body interaction if you want to count your gravitational radiation as a third body in some sense. Even the further step would be that you then also have some back reaction of this long-range radiation back onto your two-body system. And if you're even better, you can implement, you have some models of your, it's a neutron star, that's some inner structure, also that it can deform, and then you really can effectively describe this whole problem in a very organized way. There's two main approaches how this is done, and it has to do with these two ways of expanding this two-body Hamiltonian. So there's the first direction, which expands in v square over c square. That's your small parameter. It's called the post-Newtonian expansion. And this actually started a long time ago, already in 1917. Then probably the first interesting result was actually by Einstein, Infeld, Hoffman. That's written down the first correction to the Newtonian potential. Essentially just, again, just a conservative motion of these two bodies. Nowadays, there's actually, let's say, I would more or less categorize it into two big groups that are working on this problem nowadays. So it's maybe the first half of these people here that are really doing some type of classic GR, well, so essentially iteratively solving Einstein's equation in some way or the other. And then the second part is what you might have heard about, is this energy GR type of construction, where you really do an effective field theory where you integrate out the gravitational field in the classical limit, and you can then compute exactly the conservative potential. You can also include radiation reaction, and so on. But I'm not going to talk about it too much, because for me, more important is the other type of expansion. That's actually something I'm more used to, since I'm coming from the scattering amplitude side. So we are used to expand all our quantities in powers of the coupling. So for gravity, this would simply be g Newton. That means that essentially what this means, that if you compute something, the post-Minkowskian expansion, you resum the velocity correction at some fixed order in g to all orders, which of course then essentially gives you, in my equation over here, the whole line at once. So you have the whole resummed tower of velocity corrections at once. Again, there's two, let's say, basic philosophies how you can do that. As before, you can just do it simply doing some classic GR. Again, you expand the equations of motion order by order, plug it back in, and you compute an effective potential between the two bodies. Or something that has just been recently started is that you use scattering amplitudes. The reason is that in this big field of scattering amplitudes, there's a lot of very interesting technologies that help you a lot to compute the scattering amplitudes. And as it turns out, once you have computed some gravitational amplitude, it's not too hard to extract some data out of it that can be used to describe this orbiting problem. And that's actually what I will be focusing on for the rest of the talk, how we can take the scattering amplitudes and extract data that is important for our gravitational waves problem. Maybe we should also mention that there's a third sort of expansion you can do. It's called this gravitational self-force. The idea is that you expand now in terms of m2 over m1, where one of the bodies is very heavy and the other one is very light. Also, that has started quite some time ago. And I guess if you're interested, you should look up some of these people's names and see what they're doing. Okay. To just give you some impression where we stand these days, this is actually a slide that I've stolen from Alessandro Buran's slides from the Amplitudes conference from 2 years ago. So back then, actually, this blue line was one further up. And this is the state of the art for just the conservative potential. So none of the bodies are spinning. There's no radiation involved or anything. This is really just the simplest description that you can do. So here, this is as the amplitude I showed you before. It's 3 p.m. right now. So up till here, everything is known. And of course, all the whole tower towards the right here is known just through these PM computations. The 4 p.m. is the only one that is completed for the conservative potential. Some parts of 5 p.m. are actually done. I think right now, at least the 3 p.m. correction has been done. Also in 6 p.m., I think this correction until here, until v to the power of 8 has been done. But there's actually a very interesting story related to that, because there's a claim that this 3 p.m. computation from the amplitudes has some problem if you go to higher orders here. So there was a paper by Thibaut Damour a couple of 2 months ago, I think, where he claimed that there's a problem with the high energy limit of this amplitude computation. Just to give you some impression that there's still some debate whether all these results are correct or not. All right. Okay. So now let's go back to a problem that we had before, just give you some impression. But then afterwards is done, once you have described the first part of our in-spiral, then you want to continue to the merger. And there, of course, our perturbative expansion in part of G or V squared, whatever you want, completely fails, because we're now in a completely different regime. We have high velocities, we have high energies, and we cannot simply do a perturbation theory. For that part of the problem, people really have to rely on numerical relativity simulations. And the simulation I showed you on the slide before exactly is one of these type of simulations. So what people, of course, do that you just want to map a big part of your phase space. So for different masses and different starting parameters of this in-spiral, you really want to compute this waveform. And then you just map the whole space. You repeat the same code until you have mapped out your whole parameter space that then can be used by experimentalists to really match it to observe the patterns that they have there. Finally, for the ring down, what people are doing here is simply some so-called black hole perturbation theory. So you simply describe the modes of your black hole, or you can even do something similar for the neutron star, it's just a bit more complicated. Just have one body that is now, we have now some fluctuations, it's now just moving into one or the other direction. At the end of the day, though, you still want to have one full waveform. So this whole package, in the end, you want to describe this whole waveform from the start to the end. Of course, you have now a problem that for the in-spiral and for the merger, you'd always talk about 2 bodies. But in the ring down, you're back to only describing one body. So this has been solved by Bonan and Damour, is that they also have rewritten all this input from numerical relativity, from the PN expansions, from PM expansions, as just an effective one body that is moving in an effective background field. And through that, you can exactly get this type of waveform that I showed you today. These guys here. So once you have all the input data from all places, you merge it into one single object as one single effective body that moves in some background field. All right. Okay, let me get back where I was. So for the rest of the talk, I will really be focusing on the scattering amplitudes computation, or better, what you can do with the scattering amplitudes results once you have them, and what you can, well, how you can somehow get observables out of it. So let me describe how these people are actually doing it. So how do they get something out of it that can be used for these classical gravity computations? So how it's done is that I start by really considering a theory like here. So this is something we'd call the full theory. So I model, let's say, my black hole or my neutron star as a scalar field. Okay, so my phi, I have 2 phi, so I will have 2 bodies of some types, just 2 scalars that interact gravitationally with each other. To compute the amplitude, of course, you can just do a Feynman computation. Of course, these people are much cleverer. They can use fancy technologies like unitarity cuts, you have BCFW, recursion relations, whatever you want. All right, so these people are very good at doing that, and they can compute it now. That's the state of the art, that they can compute this 2-loop amplitude. What is then done that you want to somehow match this to an effective description. All right, so what you write down here, we just go to some simple, well, again, you have two scalar fields, but now they just have some non-relativity interaction. So I just write down some generic potential and some 5-4 coupling. So this should essentially correspond to sort of by integrating out the gravitational field. Of course, here now, even at order, let's say g cubed, over here, I will have several diagrams that go into it. Okay, that I can then, at the end of the day, I can match to my full theory computation. Maybe something that's important here, that we only care about the classical part. So even on the full theory side, you can be a little bit careless and throw away everything that is obviously quantum. So if you have some internal graviton loops, you can immediately throw it away. You can also be very clever by doing the integration in a let's say, integration by region. So you really look at the regions that are interesting for the classical long-range interaction. But at the end of the day, you simply just match these two amplitudes and you can find your effective potential. So that's great, because once you have an effective potential, you can immediately write down an effective two-body Hamiltonian. Let's say something of the form like this guy here. Of course, there's no radiation anymore. This is simply a conservative Hamiltonian. So this is really the simplest problem at this point. But what is nice now, of course, we can, with this input, this amplitude at second loop order, you immediately have all the information up to order g cubed. So how this is effectively done is by computing the so-called CI coefficients here. So I plug this in order by order, and order by order in G, I map these two sides here. What is done an interesting effect is that, as I mentioned slightly before, that at g cubed, for example, we get the C3 here, right? Because this will exactly go in at order g to the third power. But also this diagram will contribute because it can, for example, put the C1 here and the C2 over here, which will also give a contribution to g cubed. And also here, of course, you have the C1, and the C1. What happens now that these two diagrams here will exactly reproduce the IR divergence part that you will, of course, have in your gravitational amplitude. So order by order, you can somehow cancel your IR divergences in a very systematic manner. And the resulting guy, for here, for example, would be the C3 guy, is then a perfectly classical and finite quantity, which is, of course, what you want and what you would expect should come out at the end of the day. Okay, very good. So now let me actually come to the part where Raphael and I have been working on. So for the rest of this talk, I will really focus on this graphics here. I'm trying to explain you all the different links between all the quantities that we have here, that to explain how, at the end of the day, so this is where I want to get are these observables here. These are just some, for example, some frequencies. I want to describe the whole geometry of the orbital problem by having one simple input. And the one simple input is my amplitude over here. Exactly the amplitude that I've described for you on the slide before. So as the story will go, that I first will describe somehow how can we extract a scattering angle from this amplitude. So on this side here, we are still on the scattering side of the problem. So still you have positive energies, you have two bodies coming in, they scatter, they go away to infinity once more. What it becomes much more interesting is if you go now to the orbital problem. So first of all, we can find some connection to a thing called the Periosteum advance. That means how the orbit, if you just could have some effective description. So this would here would be one of the particles, and the other particle would go around it in the circles. So how this ellipse is turning around on the plane, so in space. Related to it, we will see how we can directly compute this radial action. So for those of you familiar with Hamilton-Jacobi formalism, this is simply the radial part of the Hamilton-Jacobi action. So for those who don't know, you might want to go back to your classical mechanics note and look it up, what this exactly means. It's just a very interesting quantity And from this radial action, we will be able to extract all of the information that we need to really completely describe this binary inspiral problem. As already mentioned before, exactly, I will just talk about conservative motion, and I will only talk in the end a little bit about spin. So there's one special case where I can also describe this whole diagram actually for spinning objects in space. Okay, are there any questions so far? Okay, if not, then let's get started with this first link here between the amplitude and the scattering angle. So something that we noted at some point, which was actually a little bit hinted to by this amplitudes paper by Byrne et al., is that there seems to be a very nice relation between p squared. So this p squared, maybe let me go back, what this p squared is. If I have my Hamiltonian here, for conservative motion, I can solve this equation for p squared as a function of the energy and of the radius. Okay, so this will be some of my momentum along the trajectory of one of the bodies, or to be more precise, in the center of mass frame of these bodies. Okay, and the claim is that the square of this quantity is more or less equal to the scattering amplitude in position space. So what I need to do Fourier transform my momentum space amplitude. I need to normalize it by some energy factor, and then it's essentially the same as this dynamical momentum. This p infinity here is simply the scattering momentum at infinity. Okay, so it would be what's like, okay, if you study the scattering amplitudes, that's essentially the momentum that you would plug into your scattering amplitude. Okay, so actually a little bit after us, there are also these people here that have realized the same identity. They proved it a little bit different from us. So if you're interested, it would also be good to look into this paper if you want to see some of where it's coming from. But just let me sketch how you can see why this identity should be true. So let us for a moment consider some potential scattering. Okay, so what I can write down is some sort of an effective, some sort of Schrödinger equation for this problem. Let's just say given some effective potential, and I want to compute my p squared on the trajectory for this problem. So of course, classical mechanics will tell me, well, you can now solve this equation, you can compute this psi of p, and you can compute a scattering amplitude by just simply sandwiching the effective potential inside, well, with a solution and some free momentum state. Okay, that's what I would call an amplitude for a potential scattering. What I can do now is to write the solution for my Schrödinger equation over here in a Lippmann-Schwinger type of solution. That means I just iteratively plug in a free momentum state plus, again, iteratively my solution that I have. If you now think about that, this effective potential is expanded in powers of my gravitational coupling. In the case here, you can solve then this equation over here order by order in G. Okay, the only thing you need to do are some integrals of this type here, of this Lippmann-Schwinger type. All right. So if I plug this in and expand, so I would expand my my amplitude in powers of G. So this Fn would still be the coefficient of the G to the n term, and my V effective n would simply be the coefficient of the G to the n term in my effective potential that I write down. And of course, I will get a whole tower of iterations at each step. What's now interesting that this iteration are very similar to this iteration that I mentioned for the scattering amplitude. So there we have been iterating somehow this EI coefficients in the EFT. What we now iterate here is somehow the lower order amplitudes and the lower order effective potential. What gives us at the end of the day our impetus formula is the observation that these contributions here are purely IR divergent. And even more, they're super classic. So that means there's quantum contributions, They're classical contributions, and they're so-called superclassical contributions. So those are contributions that are even more classical. They come with a, let's say, better power counting in H bar than the classical contributions. Naively, of course, you wouldn't expect them to be there, and they are not there in every physical answer, but you need to be very careful to subtract them out properly. All right. So if I now define my finite amplitude here by just killing off all my IR divergences with this term here, I can simply ignore it and write this answer here down. So my amplitude, if I just, let's say, match it with some cross-section, let's say now, well, my effective problem should describe the same physics as my actual QFT scattering amplitude. I can immediately conclude that my scattering amplitude is equal to this effective potential. But by my equation at start, of course, I know that my minus my effective potential is equal to p squared plus this minus p infinity squared, which leads me immediately to this impetus formula. So in different words, it says that the Born approximation for this Lippmann-Schwinger problem is exact in a classical limit once you have properly defined what you mean by an IR finite classical amplitude. All right, that has actually been a paper a couple of weeks ago by some Nodita people that have exactly proved that this type of subtraction here is exactly the same as the subtraction that you're doing with the amplitude matching to the EFT. These are two completely equivalent approaches. It's just that this approach here gives you nicely this relation between the amplitude and your p squared. Okay, so now I promised you that we will go to the scattering angle from that. Oh, maybe exactly first, just to give you some idea how it's actually done, how it's actually useful to do computations with it, is by doing this PM expansion, the post-Minkowski expansion. We're doing expansion in powers of g, and for notation afterwards, I will call the coefficient of g over r to the power of n, this mn tilde, and then I have this pn coefficients in the expansion of my p squared. So you can remember that mn and pn are more or less the same, exactly given by this impetus formula. All right, so now it's actually very easy to compute the scattering angle from this. If you do some classical mechanics, sit down for a moment, you can find this type of formula here. So once you have this momentum along the trajectory in the center of mass frame, you can immediately compute your scattering angle chi on the left-hand side here. But since we know that this p squared is equal to the amplitude, well, we can simply replace it and plug it in here. The only missing ingredient actually is this r min. So physically, this is, if you consider the scattering problem, this is the shortest distance between the two bodies in the middle when they almost meet each other, right? But also that this is determined by solving this equation here. So I need to check where the radial momentum squared is 0. Okay, and this is simply that you have p squared is equal to j squared divided by r squared, where j is your angular momentum. But also that, of course, once more, we know p squared in terms of the amplitude, so we can take our amplitude, we can plug it in, and we're done. We can simply compute this more or less simple one-dimensional integral. Again, how you would practically do that is that, so, okay, just to need a little bit of more notation, unfortunately. These coefficients are mostly called Fn that you're gonna use. So it's simply a rescaling of your amplitude coefficients. So again, you should remember Pn's are the same as Mn's and Mn's are the same as the Fn's up to some normalization factors. What you can do, you can explicitly solve it order by order, and you find expressions like that. So again, I expand my scattering angle. This chi bn's are my coefficients of g to the power of n. Okay. So now I've expressed my chi bn's in terms of my fn's. Let's maybe look a little bit closer to it, because this is a very interesting formula. What I sum here over is partitions of n. So it's integer partitions. So what I mean by that is that I want to have all the sigmas here that add up to n. So the sigmas with lower indices should be unique numbers, and the ones with upper indices should just be some integer number. Let's do a simple example. For example, if I want to compute chi3, so my n is now 3 over here. I can first of all have that this guy here is 3 times 1. Okay, so let's simply have f3, f1 times just some combinatorial prefactor. I can write n as 1 times 1 plus 2 times 1. So we'll have f1 to the power of 1, f2 to the power of 1, with again some combinatorial prefactor. And finally, what I can have is that I can have 1 times 3, which would give me my f1 to the 3rd power, which gives me the last term in this expansion over here. So it's actually very important what the form is, but note something interesting, that the chi-n depends in general only on the fn's and all the smaller f. So fn minus 1, fn minus 2, and so on. So it's the whole tower that is chi-n's depend on, which will be, try to remember that because it will be important towards the end of the talk, but I will come back to that. So the upshot here is really that you can immediately solve it. If someone gives you this fi's, so these are simply amplitudes, you plug it in, you can get this scattering angle to arbitrary order, and your computer algebra system will do it for you in seconds. Okay, so now we can also invert this whole problem. There was an interesting paper by Firsov in 1953. I actually haven't been able to find the original paper. It's published in some Russian journal, and it turns out that it's not digitalized, so you cannot actually find it on the internet. But it's a homework problem if one of the Lipschitz classical mechanics books, and there he exactly derives this formula here. So what you have to do, you have to look at the formula that we had before. Angle. Oops. This formula here, and you can pseudo invert it for the p squared. So here, of course, the integral boundaries and the guy down here still depends on p squared. But as it turns out, if you can easily solve it iteratively again. And you can now express fn's in terms of the chi-b's. And the sums is again very similar, that you will have a sum over the same type of partitions as we had before, times some combinatorial prefactor. All right, so these guys look very similar, and you can actually plug it in to the equation I found above, and you see that it's the actual inverse of the written.
Sorry,
before.
Gregor, can I ask a question?
Sure, yeah.
So B here is your impact parameter, yes?
That's right, yes.
What's the range of your impact parameter? Does it extend from 0 to infinity, or is there some bound?
That's so okay, actually, if you wait maybe for 2 slides, I'll actually explain the geometry a little bit better. If you just bear with me, then you'll see what I mean by this impact parameter. That's a very good question. Yes, well, I'll get there, I promise. Okay. So just as the interesting remark here, you can also, if you solve this Armin condition, you can find an equation like that. And this equation, it's now a direct relation between m and chi. What is interesting is that it somewhat looks like an iconal exponentiation of your scattering angle here. It's not exactly the same because we have a d3 integral, not a d2 integral, as you would expect from some iconal approximation. But still, it looks very similar. And we don't quite know what's the relation between the iconal story and what we are doing here. So this is something that might be interesting in the future to look at and explain a little bit better. All right. So the next thing I want to describe is the link between the scattering amplitude and this radial action. So maybe before I actually do that, then let me just answer your question. If I look at the geometry of this problem, so that's what I will have in the scattering case. Exactly, B is my impact parameter. So it can just vary what it wants from 0 to infinity, essentially. Of course, if B gets too small, then my perturbative expansion is not good anymore. So of course, I expand in something that gets big. So it's not valid anymore. So this should be a rather big quantity for my perturbative series to be correct. But otherwise, it's just a real number in general. What I can do now the only things that I need to compute are the scattering angle, which you just had before. I know how to compute it from the scattering amplitude, and this minimal distance. Okay, before I call it R min, but you can also call it maybe R min tilde, just to have this graphic nicely explained here. And by the formula I showed you before, by Firstov's formula, you find an expression like that. So I can express this R min in terms of the scattering angle, which in turn I can express in terms of the scattering amplitude. So once more, this problem is perfectly solved by this formula here. This is simply the PM expanded form, where again, I just write it in terms of chi b ends. What's now an interesting step that you can do is that you compare that to your orbital problem, or to your spiral problem, where you have two bodies that are bound in a closed system. So the identity that is crucial is this guy here, where I express the angular momentum in terms of my impact parameter. So if my impact parameter is positive, and if my p infinity is a real number, this guy is of course also a real number. So what happens now if I go to this bound problem, my p infinity squared will become negative. That means that my p infinity here is an imaginary number. At the end of the day, the physical quantity is my angular momentum, which now you can conclude that, of course, b better be also, imaginary number, which sort of makes sense. You can think about, okay, you have a scattering problem. Of course, it only makes sense to talk about an impact parameter if you have a scattering. But if you have now a bound orbit, you can say, well, maybe it just corresponds to have an imaginary number here. And indeed, if you do that, so before I have written this R min in terms of this impact parameter b squared. Okay, what I can do now, I can just write it in terms of j, which is again a function of b, and I claim that now the smaller radius between these two bodies, so you have to think about that this body here moves on this smaller ellipse around, and this body here, the second, moves on the bigger black ellipse, and the gradient here is simply the center of mass. Okay, and here in the middle, that's where they always meet, where they're closest to each other. This R minus can be simply expressed as an analytic continuation of this formula over here. Similarly, interesting, if you swap the sign of b, because a priori you don't really know what the correct sign should be here. If you swap the sign here, you find the R plus, so you find the bigger radius. So this whole distance here, where they're furthest apart from each other. And you can express it again in terms of this R min, by simply swapping the sign. Equivalently, actually, this means that this R minus and R plus are the two real positive roots of this polynomial here, of the angular momentum of our classical description. Okay. If you think about it, this is quite astonishing. Because what I claim for you, that if you have an arbitrary order n polynomial, taking this formula over here, you can find two of its roots, which I actually thought is impossible by my basic algebra knowledge that I had from math. So apparently, if you really, so of course, there's one catch. You have to be careful that here, of course, that's an infinite sum. So you really need to do this infinite sum at a given order in n. So we'll have infinitely many terms that we need to resum. But if you can do it, and for some cases we can actually do it, you have a closed form expression for this R minus and R plus, i.e. for these positive roots of an of a third order polynomial, which of course is not too surprising, but if you can continue to higher orders, you can find two roots of an arbitrary order polynomial. So also then, this problem is actually completely described if you have R plus and R minus, because you can compute the eccentricity, you can compute this A factor here, everything is described in the problem. You completely understand the whole geometry simply by inputting your scattering amplitudes, order by order in G, of course. Right, and then to show you this funny picture, so that's how it would look in motion. The time scale is not correct, so it's just some arbitrary time parameterization, but otherwise, this is a valid configuration of two black holes orbiting each other with this geometry. Perfect. Okay, so I actually need to go back that you see the whole slide that I skipped before. Yes, this guy here. So I promised you that I want to go from my scattering amplitude to the radial action. But this radial action for this two-body problem has been studied by these three people here 20 years ago. And if you just study, it's more or less, it's quite simple. Analytical mechanics you have to do, you can write this radial action as simplest integral from now exactly r minus and r plus in the orbital case of your orbital momentum. So expressed a little bit differently, you simply have to do this integral over here. Since we have our impetus formula where you can express p squared as a function of the scattering amplitude, the line here shouldn't surprise you too much. That means we can immediately compute the radial action once we are given the scattering amplitude. Okay, now I need to skip through that again. And of course, how it's practically done is by doing the PM expansion in powers of my gravitational coupling G. What is easy to do is actually if you, okay, this looks a bit more complicated than actually should be. All these functions here are simply functions of the amplitude. So A, B, and C are just, okay, that's just some constant factor. We have the one loop amplitude and the three level amplitude. And then we have all the higher loop amplitudes in this DL coefficient. So this is just this guy rewritten, study different notation. What I will expand now is actually in this lambda parameter. That's just an artificial parameter I introduced to do it. So if you do this expansion in this lambda, you will find this ugly, huge, disgusting formula. At the end of today, you have this radial action here, which now depends. This is just, again, a very similar sum over integer partitions as we saw it before. We have some just combinatorial prefactor. At the end here, we have powers of the amplitude. This again with just some higher loop order amplitudes. And finally, a thing that we call master integrals, which are simply hypergeometric functions in terms of A, B, and C, which were our three level and one loop amplitude. Okay. So now, if you write it down, this is essentially a PM expansion radial action. Very simply, it's simply a format you can take, you plug everything in, and you can compute it within seconds once you're given your scattering amplitudes. So this is great, because now even more fun starts, and we can do a lot of more things once we have that. But first, before I get there, you can do a very similar story to compute the Periosteum advance over here. So somehow, what the scattering angle is for the scattering problem, the Periosteum advance is for the bound problem. The scattering angle is more or less the same as the Periosteum advance. To show you how you can see that. So if you think about in the scattering case, I gave you formula for chi in this form over here. Okay, that's the formula I've written down a couple of slides before. If you now somehow compare to the formula for the radial action, this pretty much looks like a derivative of this radial action with respect to j. Okay, just that you have some different boundaries. You have r minus to infinity instead of r minus to r plus. Now for the closed orbit case, where I have negative energies, that's exactly the formula I've written down for you at the page before, and I've taken the chain derivative to compute my Periosteum advance. This is simply the definition of the Periosteum advance. If I compare these two formula and remember what we told about the relation between this r minus tilde, so the minimal distance between the two bodies for a scattering case, and the two radii that describe the bound problem, then you can immediately find this formula here, the relation between the Periosteum advance and the scattering angle. So here I essentially really just added up two copies. Well, I plug in r minus here, I swap the sign of j, I get the r plus, I add them up to somehow subtract the region between r plus and infinity, and I immediately end up with the Periosteum advance. So this is very simple once you actually have all the formula that we have found before. Of course, we can do it again nicely in the PM framework, and you find nice formula for the Periosteum advance in terms of the scattering amplitude. Okay. Maybe one important point here for the experts is that at order j to the minus 4, so j is just some rescaled angular momentum, we're going to need the 3-loop amplitude, which is not known yet. So what is known is the 3-level, the 1-loop, and the 2-loop amplitude. So this guy is not known yet. So to complete this formula here at order 3 to the -4, really going to need this next order here. And this is the same story that actually this contribution here is known to some order in the velocity, which is the 3pn, so the post-Newtonian contribution is known, but of course not to all velocities. So here, that's probably the most interesting part to look at if you're able to compute the 3-loop amplitude. Okay, perfect. So before I go to the observables, to more observables actually, I want to close some of the circle here. Because I said we can get from the radial action to the scattering angle and to the Periosteum advance by taking derivatives. Of course, we can do the opposite and we can integrate up. So either we can integrate the Periosteum advance or the scattering angle. Again, they're more or less the same, so it doesn't really matter which one you're going to integrate. You can do it. You can take the formula that we had before of this radial action in terms, okay, exactly. You take your scattering angle, you integrate it up, you find an expression for the radial action in terms of the scattering angle. Okay, it just looks something like that in the PM formalism, and you need to introduce, of course, you need to find the boundary term, which you can get from the first computation where we computed the radial action in terms of the amplitude directly. Okay, so it's just indirect way, because again, I can express the scattering angle in terms of the scattering amplitude, and I can find, once more, quite neat expressions. Of course, here the same problem appears again. Of course, it's not shifted because I divided by, well, I multiply by j. It's not the j to the -3 terms is only complete with the 3-loop amplitude. Also now, of course, this expression here looks sort of much nicer than this huge formula I showed you on the slide before, where I compute the radial action in terms of the amplitude directly, but they're equivalent. So if you plug in here the formula for the scattering amplitude, you can show that these two expressions coincide. At least, well, in the PM framework, you just do it order by order, you can prove it quite neatly. Okay. Very good. Now, finally, we can profit from all the hard work that we did, because to get a lot of observables out of this is now a simple game of taking derivatives. In the same paper, people discussed radial action. It also described a lot of interesting observables for this bound problem. We already said we can compute the Periosteum advance by taking derivative with respect to j. Then the period, so okay, I do have my picture here. So the period where these bodies go once around until they meet again in the periastron, this period can be computed by taking the derivative with respect to the energy. Then, of course, the related frequency, simply 1 over this guy here, is of course easily computed by just taking the 1 over TP. We can compute the periostron frequency. So that's the frequency, how fast the periostron moves. Okay, so it's the point where the two guys are closest to each other. So how this guy moves around in your plane very slowly. You can, which is computed as taking, well, the Periosteum advance divided by the Periosteum period. Finally, you can, of course, trivially just add up these two guys, the radial frequency and the Periosteum frequency, to get the, let's say, the absolute frequency, how each of the body moves, let's say, around the center of mass in the middle. And finally, you can also compute the observable called the average redshift, which I actually don't have time to talk about, but you can read it up in this paper by Letiec. So it's the only other some derivative you can imagine that you can take a derivative with respect to the mass. Okay, and to give you some idea how this now looks, so it doesn't really matter what exactly is there, but you can now plug it in and you can compute the, for example, this Periosteum advance in terms of the energy. This gamma square is simply the relativistic velocity factor. This capital gamma here is the energy divided by the total mass, and again we have our angular momentum j here. So this is if I take the 1, 2, and 3-loop amplitude, sorry, the 3-level, 1-loop and 2-loop amplitude, and plug it into my formula. And this agrees with all known literature on the topic from the PN and also previous PM computations that people have been done in the past. And then again, for the experts, I can make the same comment as before. If you compare to a 3PN approach, so the post-Newtonian approach, we don't get all the 3PN terms right, let's say for the radial frequency. The problem is again that we're missing the 3-loop amplitude. So some of the terms, the blue ones, are the ones that agree with all the 3PN literature, but we're missing a contribution at 10 to the minus 3. Again, this E is just some rescaled energy that is typically used in the classical general relativity community. And of course, we also get some contributions to higher order terms, to let's say for PN contributions in the velocity, and the same also for the other angle. Okay, so the upshot here is that we agree with this approach with all known result in the PN literature as you would expect it to the given order in the velocity and the coupling G. Okay, very good. As I promised you, towards the end, I can also talk a little bit about the spinning case. So this is in the second paper. I already discussed this case a little bit. There is one special case where we can include the spin in the problem. That here. Again, it's just conservative motion. I'm just computing conservative quantities like the scattering angle or the Periosteum ones. So by aligned spin, I mean it's classical spin, so it's no quantum spin or anything. It's really just classical spin of the two bodies. It's in the same direction, and it's orthogonal to the plane of the movement. So still, the motion of the two bodies still happens in a single plane. As it turns out, you can write down a very similar formula that relates the Periosteum bonds to the scattering angle. There's one little difference, which is that you have to take the complete, so the total angular momentum. So you have to add up the orbital angular momentum and the spin angular momentum of these two guys, and then this equation is actually correct. Maybe just give you a few comments. We did some explicit checks, again with the PM results as before. Everything checks out there. You can do a similar story actually for the impetus formula. So where we relate the p squared on the trajectory to the amplitude. We cannot really check it to high order, so we can check it at 3 level, and we did partially the check for the 1-loop amplitude. But these amplitudes are a little bit tricky, and people don't quite know how to compute them at this point if you have a spin. There is some work exactly. People claim that the 1-loop amplitude is known, but it's written in a very quirky form at this point. So I really hope that this can be improved in the future. This is really an interesting problem actually to look at. Yes, okay, can I say a little bit about why this should be true? The idea is that if you remember how we proved this formula is that we swapped J to minus J. So essentially what we need to have, that again, I can relate the two radii by simply swapping J and minus J. And as it happens for this aligned spin case, you can still write all your PR, so the radial momentum, in a quasi-isotropic gauge. That means that your radial momentum only depends on combinations P dot P and P dot S. There's no, where S is the spin, and there's no P dot R terms or anything of that form. And if you think about it, there cannot much happen, because if you have it in a form like that, the whole integrand that defines your radial action or your Periosteum bonds is invariant, except for the J upstairs that gives you the correct minus sign that you would expect to prove this formula here. This somewhat nicely connects the whole story with the amplitudes, because if you compute an amplitude, you happen to exactly land on this quasi-isotropic gauge. Because if you just do some random PN, PM iterative computation of the Einstein's equation, just iteratively solve them, you will just land on, well, whatever gauge you have chosen. It's not quite clear how we can immediately get this quasi-isotropic gauge out of it. But from the amplitude's point of view, you just get it for free, which is a very nice part of the story here. All right.
Can I ask you a question?
Yeah, absolutely.
How do you know what happens if the spins are anti-aligned?
That's still fine. The magnitude doesn't matter. Okay. So you can also have the opposite case. That's right.
All right,
so
great.
The motion needs to be in a plane, and they always need to appear in squares essentially. And that's still the case even if they're anti-aligned. Yep.
Okay.
An interesting case, so that's more because that's of interest for the observations, is the circular orbit case. So what we need to solve is, of course, that two radii should be the same for the bound problem. So I want to solve the equation that r plus is equal to r minus. If I take my formula that I've given you before, as r plus is a function of the scattering angle, I get an equation like that. Once more, you can solve this equation order by order in G, and you can solve it for J, so for the angular momentum as a function of your binding energy. And you can then, for example, compute some radial frequencies and some other things. What is so interesting here is that you need to be very careful if you want to have a consistent scheme. So that's why I told in the start that the chi b, so the chi n, depends on fn and all lower n's. Okay, that means if you look at this sum here, even if I say, well, I don't know my higher order amplitude. So let's say I set my f3, f4, f5, f6 to 0 because I don't know them, I will still have infinitely many terms in my sum here, because each of the chi n to any order depend on my f1 and f2, for example. That means to consistently compute, for example, this the radial frequency for the circular orbit, you really need to do this infinite sum here. So we need to resum all contributions. And this turns out, okay, maybe that's just a result. That's very interesting, since you probably most of the time. You have to do resummations. And this not only holds for the circular orbit case. If you just want to have consistent results, you always need to resum these contributions if you really talk about the proper PM expansion. So as I said, let's do the simplest case. If I set everything except my tree-level amplitude to 0 and plug it into the formula for chi, and then compute this infinite sum, you will retrieve these Arcus tangents here, which is nothing else but the Newtonian scattering angle from simple Newtonian physics. So this is just tree level. Already at one loop, if you had the one loop contributions, you can do this sum, and it resums into, well, close form, something like that here. Again, it only depends on f1 and f2, but it has, of course, infinitely, well, it has contributions to g to the power of arbitrary n in principle. Unfortunately, as you see here, the next line is missing because I could not do the resummation including f3. And f3 is known, it's 2-loop amplitudes. In principle, it's known, but I have no idea how to do this resummation. So the statement here is these resummations would give you very nice results, give you consistent truncation of your theory, but they're very hard to do. So if anyone has experience with that, it's a very interesting thing to look at. We can also resum other observables, of course. The Periosteum advance is very similar to chi, so we will get very similar formula to the guys here. We can even resum parts of this radial action even before. So if you can resum SR, of course, it's much easier because then taking derivatives to get your observables is very simple, even if you have just a closed form. We can resum parts of the expressions for R min. So we can do the F1, F2 again for the R min and the R plus minus for the scattering and for the bound case, which again means, if you think about what these guys were, that if we really can do this resummation, we find closed forms for these roots of my arbitrary order polynomial. And maybe that's related to it, that this is very hard to do because it's not known, or there's no formula known that would give you just positive roots of an arbitrary polynomial. Okay, since I'm almost out of time, let me just conclude here at this point. I hope that I could convince you that what we're doing here is some more direct path from the amplitude to your observables. We never need to compute any gauge-dependent quantities, let's say like an effective potential, like an effective Hamiltonian. Of course, in the derivation we used it, but at the end of the day, it's completely unnecessary to compute it explicitly. You can directly go to your final results. The only thing you need to do is take some derivative, do some analytic continuations, and you're going to be happy. Still, one problem is that you need to get your amplitude. And there, the tricky computation is to extract your classical part. So you really need to do this IR matching to extract out your IR divergences to get everything correct at the end of the day, that you have well-defined finite quantities. Furthermore, I always gave you two versions of each identity. So there was always an exact version, a non-perturbative identity, and one that does the perturbative expansion. If you now, of course, could do some numerical studies, let's say you have some numerical expressions for the scattering angle as a function of your impact parameter and your masses, you could immediately plug it into a formula, and you could get out your frequencies from which you can then derive your waveforms. Of course, you need to have the full spectrum because you need to integrate over the whole B, or the whole space of B's that you have, which is of course hard. But again, I'm sure there might be some very clever people around where this might be interesting for. I talked about the problem of resummation. That's definitely something that might be interesting in the future. It actually turns out that most of these resummations are hypergeometric functions. So in principle, these are known objects, and I'm sure that they can be studied much better than we have been doing it so far. And furthermore, of course, we would like to extend this whole picture for aligned spins, for arbitrary spins, the radiation reaction. There's a lot of work going on also in the amplitudes community. I try to implement also spinning amplitudes. It's not 100% clear what you should do. Mostly it's not quite clear what type of particle you need to take. So for this non-spinning case, we took just simple scalars that were minimally coupled to Einstein gravity. But for the spinning part, it's not 100% clear what type, how you should couple spinning particles to gravity. Also, furthermore, of course, bear in mind that it's the classical spin that we want at the end of the day. So this can be up to arbitrary order. I'm not talking about quantum spins. This is a quite hard problem. Finally, that's something that we are actually thinking more about these days. If instead of doing this hard work and computing the amplitude, if we can somehow go back to classical GR methods, but stay in the PM framework and not compute not compute the effective potential, which is gauge dependent, but instead compute the scattering angle, because that guy is perfectly gauge independent, well-defined, observable. So if we can directly get there, it might actually help us to do the very same things. Because again, if we have the scattering angle, we can compute all this type of observables. So that's hopefully something that will come out in the future. It's also work with Raphael and one of the postdocs at DESY, Sheng Wen. And we're trying to implement some sort of four-line formalism to compute the scattering angle directly. Okay, I think that's it from my side, and thanks for your attention.
Cool.
Thank you very much.
So I've got a question. You mentioned in the beginning that you can use this for inspiraling black holes, but also possibly for neutron stars. So
yes.
Does that mean that you can try and understand something like tidal forces or compute love numbers or something like this? Or
yeah, that would be an extension of it. So far, of course, at the order that we look at, the tidal deformation does not yet matter. So we need to go to higher order. So it comes into play at 5pn order. And at this point, so of course, what you need to do, you need to write down some amplitudes that would incorporate these. At this point, it's not, we don't have any inner structure in the amplitude story so far. How this is done actually is with this EFT approach in non-relativistic GR, inner GR, and there they have inner structure. And you could do the same there. You could just compute the scattering angle in this NRGR formalism, and you could use the rest of the relation, of course, to compute your observables. So you just either need the scattering angle or a scattering amplitude to do the whole rest of the story. That's what I mean. We can also use it for neutron stars, just that it's not the amplitude input, but it's the EFT NRGR input that you would use.
Okay. And what you're saying about the spin, because if you take a scattering amplitude, the spin is normally encoded in, units of h bar or something at some loop order. And presumably you do some perturbative expansion and you look at some particular order in A, the spin parameter.
That's
and in
right.
the scattering amplitudes literature, you typically take the infinite spin limit, where you take something like SH bar goes to infinity, right? Where you're taking kind of H bar goes to 0 at the same time as you take the spin to infinity to get some finite answer. Are you doing a similar thing here when you get this, or are you?
Well,
you could also just look at it order by order, right? You could say, I'm just going to couple a spin 1 particle or something like that.
Exactly, that's what you're doing. That's the only thing that is known. It's the first order in spin that is actually done where you can explicitly check this result. So it's this paper by Alex Sokurov, Justin Wines and company, that I've actually written down the amplitudes at 1 loop, or 3 level at 1 loop, which gives you extent where you can extract the first order in spin, the first spin corrections. That's right. But again, for arbitrary spin, you actually the amplitudes are not known, and we don't know how to do all these mappings here. It's only a very special case of aligned spin where we can do it.
Cool. Anyone else have any questions?
So I have a question, and it's about when you showed the post-Newtonian expansion at the end in different colors, like red, green, and blue, and you said that the red ones were missing. I did not get that part that well. Could you explain again what is each color?
Absolutely. So, okay, maybe actually let me go to the slide in the start first.
Yes.
Let me try to find it.
Oh, exactly.
Where I explain the difference between PN and PM, the overlap, and where I don't overlap. Exactly here. Okay.
No. At the I think at the very
I know what you mean, but
no, not that.
No, but let me explain you because I will get there. Okay.
Okay.
If you give me a second. At what I mean, if you have the 3 PM answer here, you don't get all the corrections for 3 PN, so you're missing this guy here. That's what I mean. Those are exactly the red, the guys that are marked red, and the blue ones are all these guys here that coincide. Okay. I'm just missing some. I'm missing some contributions to complete the 3 PN if I just have a 3 PM result. Of course, those are known and can be put together, but it's just a comment that to complete this order, the 3 PN order, you need the 4 PM result.
Okay.
Yes, exactly. Let me go there. Can maybe say some more words. Yes, here exactly. So what's on me now? All the blue terms are exactly the ones up to this order in the velocity where I can match the 3 PN, and this guy here is exactly the one that should be corrected. So there will be some other guy up here, because there will be a correction from the 3 loop amplitude. Then would give the correct answer that we know from the P post-Newtonian expansion.
Okay, great, thank you. And another question, maybe a bit beyond what you presented, but so when you do the post-Newtonian expansion, then you can get like an acceleration, no? And you have like Newtonian acceleration and then all the post-Newtonian terms. Could you do the same with the post-Minkowskian expansion? Can you get like an acceleration term, but in a way that you expand? So. Okay.
So for example, if you think about, so the way I know it best is if you think about it in the EFT formulation. I mean, Allah wrote Goldberg-Rothstein. You could do very well the same type of EFT in a PM framework. That means the only problem why they don't do it, because they cannot do the integrals. That's really the problem there. You cannot do this 4-dimensional fully relativistic integrals. That's what's stopping us essentially from doing the full PM expansion. But in that formalism, you can very well have all your accelerations and everything. You can get all the radiation, whatever you want. It's just that it's very hard to do the integrals that you get.
Okay, thank you.
Any other questions? If not, thank you very much for the talk. It was very informative.
Thanks for having me.
Thank you.
And yeah,
Thanks, Gregor.
Seminar next week. Everyone wants to attend. Thanks a lot, guys. Any other questions? If not, thank you very much for the talk. It was very informative.
Thanks for having me.
Thank you.
And yeah,
Thanks, Gregor.
Seminar next week. Everyone wants to attend. Thanks. Thanks a lot, guys.